In this video, we want to take a look at the method of Lagrange multipliers. This is a way of dealing with optimization problems, max-min problems, where you have a constraint, right? In previous videos, we saw maximizing over a region where you found critical points on the interior and then you had to check what was going on in the boundary. Lagrange multipliers is a way of handling the boundary, right? So here's an example without actually doing the calculations, but just getting a feel for what's going on here. I've got a function f of x equals 7xy over e to the quantity x squared plus y squared. And if we restrict our attention just to the circle x minus 0.2 squared plus y minus 0.1 squared equals 0.64, right? It's just randomly drawn circle here. If we were doing this as find the maxes and mins in the region, you would first of all look for the critical points. And I can see from the topology, from the contour plot here, that there are 4 critical points. Actually, there's 5. There's a saddle point right in here, and then there's 4 maxes or mins. Now the contours aren't labeled here, so it's hard to tell which are maxes and mins, but I'm here to tell you this is the top of a hill, that's the top of the hill, and those are local minimums there. So in the region that we're talking about, there's 1, maybe 2 of the critical points, right? I can't really tell if the top of that one is on the outside or the inside, or maybe right on the edge. It's difficult to say. But so there's maybe 2 critical points that would be interesting. But on the boundary itself, there's the question of where's the highs and the lows. Right? And if you think of this as a topographic map showing you the height of the land you're walking on, and you're walking along the path, which is this circle, I can see that as I'm walking this way, I'm crossing these contour lines, which means, again, because this is the hill and this is the valley, if I'm walking this way, I'm going uphill. I know I'm going uphill, right? And then over here, I'm crossing, I'm going downhill. But there was a spot here. Well, there was a spot there where I happened to maybe get to the top of the hill. I don't know exactly. But here, I'm going downhill, and then I'm going uphill. And there was a place right in here where I'm doing neither. Right? Like here, uphill, downhill, and where's that spot where I was at a high point? This may not be the highest point of the whole graph, on the whole circle, but it's locally a high point. Right, at least from the point of view of walking along that path. It's not a high point from the point of view of the surface, because certainly if you go this way, it gets higher. But I'm not going that way. I'm staying on the path. And so on the path, this seems to be about the highest point. Right? This is the Massachusetts-Connecticut border, where the highest point in the state of Connecticut is on the border. Right, at the top of the mountains over here, but that's the highest point on the side of the hill in Connecticut. So there seems to be a very nice pattern that I can pick these high points and low points out, because it's in the transition from going downhill to going uphill where you're not going either, which means you're heading in the direction of a level curve. So the points of local maxes and mins on the boundary are places where the constraint curve is parallel to the level curves. And the way I'm going to be able to calculate with that is that to say that those 2 curves are parallel is to say that their tangent vectors are parallel, or it's also to say that their normal vectors are parallel. And this is where I'm going to be able to work with it, because normal vectors are very easily attained by using gradients. So here we go. Here is, I have this so that you can see the contours going up. Forgot I had put that in there. Anyway, here's the method of Lagrange multipliers. So to find extreme values of a function subject to a constraint, right? So this is a function of 2 variables that we're trying to maximize or minimize, but we're only going to do it on a curve. And I have the curve described here implicitly, right? This is not y as a function of x or anything like that. This is just some function of x and y equals a constant. The set of points in the plane to satisfy such an equation is usually a curve, right? And we want to find the points in the constraint. So to maximize, what we need to do is find the points where the gradient of the function is parallel to the gradient of this constraint curve. Right? That is, I'm thinking of that constraint as a function of two variables, but equal to one particular constant. So this is just one level curve of the function g. So I'm going to look at all of the level curves of f and that one level curve of g and see where they're parallel. That is, see where the gradient of f is parallel to the gradient of g. And to say that they're parallel means that one is a scalar multiple of the other. Now, traditionally, and I don't know where this started, perhaps with Lagrange, but the constant multiplier here is usually used as lambda. Right? So, but you could use anything. You could use it as a k. You could use it as, just don't use a letter that you're already used in the problem. Right? But typically they look like the gradient of f equals lambda times the gradient of g. Here's an example, a little simpler than the one up here, just to make the calculations easy the first time, or at least not ridiculous. The function I want to maximize or minimize is x squared plus xy plus y squared, subject to being on the unit circle, x squared plus y squared equals 1. So the picture over here, you can see the level curves of the function f, and then this one constraint curve, which is a circle of radius 1 centered at the origin. And I can see that there's probably a point here where we're as high as possible, and right there where we're as low as possible, and back here to high, and back there to low, right? Places where the two curves are parallel to each other, or the two gradients are parallel to each other. So anyway, I'm making the g be this x squared plus y squared, and so the curve I'm interested in is the level curve of level 1, right? And what I want now is the gradient of f to equal lambda times the gradient of g. Well, the gradient of f is a vector. The gradient of f is a vector where the first component is the partial with respect to x, so that would be 2x plus y. The second component is the partial with respect to y, which would be x plus 2y. And I need that equal to lambda times the gradient of g. Well, the gradient of g is also a vector, and that means the partial of this with respect to x, which is 2x, and the second component is the partial with respect to y, which is 2y. And so to say we have a vector equation here is to say that we have two real valued equations, because the x components have to be equal to each other and the y components have to be equal to each other. Those two equations are equivalent to saying that the gradient of f is lambda times the gradient of g. However, there's three variables in those two equations, so I need one more. But the one more equation is always the same thing. It's always the constraint equation. That is, I'm not interested in any x's and y's. I'm not worried about x's and y's out here, down there, over there, whatever. I'm worried about x's and y's that are on the curve. So I need that x squared plus y squared equals 1 for this problem. So there's three equations with three variables. And what I want to do is I want to solve them simultaneously. Now, as I'm solving, sometimes I solve for lambda, but usually I don't. Because usually I don't care what lambda is. I want to know what x and y are, right? I don't care what scalar it is that makes the two gradients, they're parallel to each other, what multiplier makes them actually equal to each other. I just need to know what the x's and y's are. I need to know where, so I can plug those into the function and find the function value to see if it's big or small. Right? So here we go. The method I quite often use is I will take these two equations that have the lambda in them and divide. And that gets rid of the lambda. Okay. So there's only one issue here, and that is if I divide, I want to make sure I'm not dividing by 0. Well, if lambda is equal to 0, it's saying that the gradient of f is the 0 vector. Well, the gradient of f is a 0 vector only at the max or the mins, right? Only at these points, which there aren't any on this curve, so I don't really have to worry about that. There's also the matter of whether if I'm dividing by this 2y, could y be 0? Well, yeah, y could be 0 right here or right there, but clearly those aren't my maxes and mins. So there's another way I can argue that this is legal to do here anyway. So what I'm going to do is I'm going to take this equation and divide, left side's divided, right side's divided. They should be equal to each other. Okay, and the lambdas cancel out. Also, the 2's here cancel out. So I've got this. Now if I multiply both sides by the common denominator, so y gets multiplied up there, and this gets multiplied over there, and I get this equation. Okay, so then I'm distributing this in there and that in there to get this, and then subtracting the 2xy for both sides, and I get that x squared equals y squared. With x equals y squared, what I have now is I have two equations with just x's and y's and no lambdas anymore. But with x squared equal y squared, I can just plug in, I'm going to replace the y squared by x squared to get x squared plus x squared equals 1, which means that 2x squared equals 1 and x equals plus or minus 1 over radical 2. Okay. And with x equals plus or minus radical 2, y, right, so that means x squared would be a half, so y is plus or minus 1 over radical 2 as well. Actually, this thing right here is to say that y equals plus or minus x, or x equals plus or minus y. So we're looking at where does the line y equals x and where does the line y equal minus x hit my constraint curve. And it would be at 4 different points. And those 4 points are 1 over radical 2, 1 over radical 2 with both of them positive, or with one of them negative, or with the other one negative, or with both of them negative. Those 4 points are the points on the constraint curve where your function is as big or as small as possible, at least locally. Right? As you're moving along those curves, along the constraint curve, you get a high point here, a low point there, a high point here, a low point there. And the question is which one is the highest and which one is the lowest. Because this curve is closed and bounded, we know that there has to be a max and there has to be a min. And so I can just plug them in and see. And what I get is, I get something that's a little too big off the screen. Well, this seems bound and determined not to let me see the right-hand side of the image here, but let's just see what happens here. You plug in these points into the objective function, the thing you're trying to maximize or minimize. So x squared plus x times y plus y squared, and you see what you get. Well, with them both positive, you get 3/2. With one of them negative, you get 1/2, because this part becomes negative. And so you get a half minus half plus a half, which is just a half. Likewise here, it is the same calculation with minus a half, ending up with just a half. And then with the minus minus, this all minus, and these all end up with plus again. And that equals 3/2. And for whatever reason, I can't seem to get it to show me this. So, looking at those, the 3/2 are the big ones. So the first one and the last one, and the 1/2 are the smallest ones. So you have, I wouldn't call them local maxes and mins, really. They're sort of local edge maxes and local edge mins, because you're still on the side of a hill. But, at least from the point of view of the boundary, you have a high point of a high point of 3/2 here and here, and you got low points of 1/2 at these 2 points. This works for 3 variables as well. Let's take a look with an example. Here's a function, x plus 2y plus 3z, and there's an ellipsoid that I want to use as my constraint curve, 4x squared plus 4y squared plus z squared equals 36. So the idea here is the constraint now, in this case, the constraint is an ellipsoid, right? So there's this ellipsoid in space. The function is a function of 3 variables. Again, think of it as like a temperature function. And in this case, it's linear in x, y, and z. So the level surfaces of this function of 3 variables will be planes. So there's planes for low values of f, and then bigger, and then bigger, and then bigger, and bigger, and bigger, and bigger, and bigger as you move across parallel to some direction. Well, the direction is the direction 1, 2, 3, because that's the normal vector here of any level curve. If you set this equal to a constant, you'd have a plane with normal vector 1, 2, 3. Right? So you've got all these planes, right? And there will be one such plane, which is the first one to hit this region. Right? There's one such plane here. And then you've got a bunch of planes that hit the region, and then there's one last one. So there's going to be a minimum, and there's going to be a maximum. Right? And it'll happen when the plane, which is the level surface of the function f, just just grazes, it's just tangent to this surface here, this ellipsoid. So what I do is I think of the right-hand, this would be the left-hand side, the left-hand side of this equation as a function of three variables. And let's call it G. There we go. And then this surface is just one level surface of that function. It's the surface of level 36. And so I say, all right, here's my function. I want, this is the objective function. This is the constraint function. I need to know when the two functions, when the two level curves are tangent to each other. And so I need to know when the gradients are parallel to each other. And so one gradient is lambda times the gradient of the other. Right. Well, the gradient of f here is a vector. It's a vector where the first component is the partial with respect to x, which is 1. The second component is the partial with respect to y, which is 2. And the third component is the partial with respect to z, which is 3. So there's the gradient of f. And then lambda times the gradient of g. Well, the gradient of g is also a vector. First component is partial with respect to x. That would be 8x. Second component is partial with respect to y. That would be 8y. And the third component is the partial with respect to z, which is 2z. And so what I need here is I need the x component of this one to equal the x component of that one, and the y's and the z's. So 1 equals lambda times 8x, 2 equals lambda times 8y, and 3 equals lambda times 2z. That's 3 equations now with 4 variables, x, y, z, and lambda, so I need one more equation. And that one more equation is, of course, the constraint equation, because I'm not worried about any x, y's, and z's. I'm just worried about the x, y's, and z's that are on this ellipsoid. Right? So now I have 4 equations with 4 variables, and I solve them simultaneously. And like the example above, I'm not really interested in what lambda is. I'm willing to know what x, y, and z are. So I typically solve these by eliminating the lambda first. Some people do it by just solving for lambda and then plugging in the other places, which works just fine. I tend to do it by division. Of course, with division, I have to say, well, is lambda equals 0 an option here? Well, lambda equals 0 certainly is not an option, because if lambda is 0, there's no way that this the right-hand side is going to equal the left-hand side of 1. Right? So lambda is not 0. Likewise, x can't be 0, because then that's not going to work either, right? That you're not going to have 0 equal to 1. So y can't be 0, z can't be 0 for all these same reasons that you couldn't have these equations equal to each other with those. So dividing here is not going to be a problem. So first 2 equations, if I divide 1 divided by 2, that's going to be this. The lambdas and the 8s cancel out. So you get 1 divided by 2 equals x divided by y, which then multiply both sides by both denominators. You get that y is equal to 2x. Okay? And then likewise, using the first and the third equations, I get 1 divided by 3 equals, the lambdas cancel out, the 8 and the 2 cancel out, leaving a 4 on the top. So 1 over 3 equals 4x over z, and z is equal to 12x. One of the reasons I like Lagrange multipliers as a method for working on the boundaries is that before you even get what the particular values of x, y, and z are, you usually get a nice relationship, right? In the previous one, we could see that x squared equals y squared, so x was plus or minus y. Here I see the relationship that y is twice x and z is 12 times x. Just we know the relationship before we even find the values. So I can plug these 2 relationships now into that constraint equation, because essentially by eliminating the lambda, I now have 3 equations in x, y, and z, but these are really nice equations that I can plug in. So if I do that, y is equal to 2x, right? There it is, and z is equal to 12x, and so now I have an equation with just x's, which I can solve. Right? So 4x plus, this is, so 4x squared plus 16x squared plus 144x squared equals 36. So I've got 164x squared equals 36. So x squared is 36 over 164, which simplifies to 9 over 41. And then you take the square root to be x is plus or minus 3 over the square root of 41. Plug the back up here in for y. Notice On the previous one, I had x squared equals y squared. So once I knew x, there were two values of y. Right? For each value of x, there were two values of y. With this relationship, for each value of x, there's only one value of y. So even though x is plus or minus 3 over radical 41, I'm not going to get 4 points in terms of y because I'm not going to use plus plus and plus minus and minus plus and minus minus. If x is plus, y is plus. If x is minus, y is minus. So there's really only one y value for each x value here. So plugging in with positive 3 over 41, I get y is 6 over 41 and z is 36 over 41, square root of 41. Right? So with the positive x value, you get positive y and positive z, and likewise with the negative x value, you get the negative y and the negative z. So there's two interesting points, which, again, doesn't surprise me because this was an ellipsoid, and the level curves, level surfaces, were all planes that were all parallel to each other. So there's going to be a first one that hit it and a last one that hit it, and these are the points of contact. Right? And so then looking at the function values, I see that I have f of this first one is equal to this, 123 over the square root of 41, and if I plug the negative, I get negative 123 over the square root of 41. Of course, this is the biggest one, and this is the smallest one. I know there has to be a max and there has to be a min because that ellipsoid is closed and bounded. It has to have a max and it has to have a min somewhere on it. So this was the biggest point, that was the smallest point. In the next video, I want to take a look at some problems from Calc 1, which we can solve using Lagrange multipliers in a much simpler fashion than what we did back in Calc 1.